our Balu Naik sir is a technology leader with over a 25 plus years of experience in electronics, embedded system, and avionics. He has contributed to several global aerospace and electronics projects across India, like Japan and USA. He has worked with reputed organizations such as HAL, L&T, Saint, HCL America, and Colonis Aerospace. He is currently the managing director of DBLNS Pvt Ltd and actively mentors students and professionals in advanced technology domains. His expertise span product development, innovation, and industry focused training. Sir, welcome, sir. Welcome to the session, Balu Naik, sir. Over to you. May you may start the session, sir. Thank you. Just
Thank you, Harsha, for inviting me. Am
thank.
I audible?
Yeah, sir.
Yeah, okay. Yeah. So, myself, Balu Naik, Deshawat. So, I work various industries actually. Most of the areas I work with. And then 2019, I came back from US and then I started my startup company. It's a DBLNS Pvt Ltd. It's a DBLNS design development lead and nation strategy. Name itself, I'm into hardware design and development area. So we are supporting majorly like electronics prototype development, like from requirement to evaluation. So at present we are having our own R&D products also. We are into medical surgical units and all, like medical devices. And apart from that, we are working few aerospace supporting services also we are working. So, and basically we are majorly in the hardware design and development area. So most of the speakers covered like product wise, system wise overviews and all they covered. So now my agenda today is like semiconductor overview and manufacturing. And next is like embedded systems and manufacturing of product development. So now coming to semiconductor. So you might saw so many components inside the LRU and the system, like what Vishnu showed. So I'm going in little bit inside the chip level. So if you see, semiconductors are like materials. It's like generated from the silicon. So it is processed in different temperatures and all, and creates like wafer. So in the wafer, again, we need to you need to build the chip. Suppose if you see any transistor, diode, like CPUs or memory chips, logic chips, all comes from the semiconductor. So to do that semiconductor chip like SoC, like ASIC chip, it won't directly go to the chip level. So actually what they do is once wafer is ready, before that they have to build the architecture. Suppose one memory chip we are developing. So we need to develop the proper architecture and then like from concept to the building the chip. So what we have to do is in this is like once architecture is defined, then we have to use the few UDA tools are there. So suppose if you see the semiconductor domain, there are so many big companies like NVIDIA, AMD, like IBM. Those are the good big players in semiconductor actually. So we have to use the few EDA tools. So in like our speakers told, like VLSI development. So majorly in semiconductor will be involving the VLSI. So in VLSI, it won't directly go to the ASIC chip. So what we have to do is like initially we need to develop the prototype. So the prototype means once the architecture is defined, we have to develop the prototype. So in prototype, we have to use the FPGA. So that is called like front end, and that another one is back end. So in front end, majorly we use like FPGA, CPLD, those logic chips and all logic devices we'll use, and we'll make one prototype development board. in the development board only, we'll realize the requirement. So once that requirement is met, then we'll have to go to the ASIC chip. Then ASIC chip will develop, and finally we'll get the one memory chip, like microcontroller or any memory chips like DDR RAM, flash RAM, any device, any component, it will come after backend. So for using for those area, we have to use like few EDA tools. So majorly in FPGA area, we'll have to use the like Model Sim, and there are Cadence tool, Synopsys, and Siemens. Those are the big players, and those tools we have to use and then build your prototype. And even backend also we'll have to use these tools, and then once like in FPGA, we have to meet the like there are major roles like clock. There are multiple clocks, so we have to synchronize each clock, and then suppose we have memory locations. So properly we have to define, and everything we'll have to test in the front end itself. So for that there are few RTL tools. So we have to develop the FPGA like RTL tools and verification. V&V is a big domain in front end. So for those things we'll have to use the tools like Verilog, VHDL, and using those tools we have to stimulate the signals. Suppose if you want to see the timing also, suppose they will give like clock, suppose 40 megahertz. So 40 megahertz timing and all we have to give, and from 40 megahertz we have to generate multiple clocks. Suppose maybe different clocks we have to generate. All clocks should be synchronized. Those things and all, once chip is developed, during that time it's very difficult. It's a huge money involved, time involved. All those things will be wasted actually. For that, they have to front end itself. We have to fix all the things, and for that we have to use different stimulation tools. With the tools, we have to create a workbench, and RTL code we have to write and then test. That is a big domain in the VLSI. RTL workbench, that is a big V&V will call actually. That is a big domain. So once that is successfully done, prototype, everything is proven, and then that is the input for the ASIC design. So in the ASIC design, again they have to do the place and route. Wafer is ready after silicon process. Then on wafer we have to embed the chip. Suppose one memory chip is there, so that memory chip again we have to embed it. There are few processes like assignments, pin assignments, and then place and route. We have to suppose you are looking like one chip. It has suppose 48 pins. We'll be looking only 48 pins. One chip is available, but inside there are multiple transistors used actually. So those and all will be bonded inside the chip. So from that we'll get chip. So that is again use the Synopsys tools, Cadence tools, and to do the place and route, because everything is bound inside, like bonding we have to do. So that is the backend you will call. So the backend is again it's a big workforce. So nowadays in the backend and all, like Intel, TI, those guys and all developing the backend software things and all. So once that is done, we'll get the chip. So that these are like, but to do all these things, students, they should have good knowledge, like fundamentals they should have. How transistor works, they should know. How PNP transistor works, they should know. When it will be conducted, when it is be not conducted, when it will be saturated, when suppose Zener diode will be, when it will break down. So all those fundamentals they should know. Without fundamentals, VLSI is very difficult. So whenever you want to go into that area, VLSI, you should have basic fundamentals, basic things like how diode works, how transistor works. Then only you can add multiple transistors inside and you'll get the logic output. Otherwise, it's very difficult. So it's a core technology, and if you know good knowledge and if you cope up your skills, then this is a very big domain actually. So this is like semiconductor. So if you see the sectors wise, if you see like consumer electronics, aerospace, automotive, and now AI accelerated machines, MEMS. Now initial earlier we have to see like chip. Now in MEMS we are adding some sensors inside itself. Suppose if any audio sensor, if you want, like audio acoustic sensor, so everything audio A to D converter and the what you call the interface, everything is embedded inside the MEMS itself. Nowadays SoCs, MEMS, like miniature components are coming. Those are all developed in the ASIC. So this is like a huge domain in semiconductor. So and coming to, yeah, these are the semiconductor area. So if you want to upskill your knowledge in this area, so you have to be very strong in VHDL coding, Verilog, and then simulation tools like multisim, RTL, bench how to create, and then some scripts also we have to write, and then test the output, test the output and get the output actually. So these are the major thing. But basically, if you want to go into this domain, you have to learn properly VHDL, Verilog, those things, and fundamentals. Don't forget the fundamentals. You should have strong fundamentals like digital electronics, analog electronics. You should be strong. Then you can go into that. Like front end, little bit uh, like software type, but back end you should have strong fundamentals. So this is like semiconductor area, and next is embedded systems. So I will tell embedded systems in two ways. Like embedded systems, people think it's big way, but embedded system is very simple thing. It's like a combination of hardware, software, and the communication. All these combinations is embedded system. Suppose if you see the hardware, so in hardware we'll have like microcontrollers, sensors, like input sensors, output actuators. Those are all comes into hardware. So to talk something with the external world or something we have to do, we need software. So suppose microprocessor is interface to the 4K by 8 memory chip. So 4K by 8 is 4K is 4096 locations. So we want to store some value inside that chip. So we should know the interface. 4K is the address, correct? So 2 power 12, or if you see 0 to 11 means 2 power 11. So address lines are 2 power 11 and data is 8 bit. So that you should know actually. Then you can interface the memory with your microcontroller or microprocessor. Suppose if you want to interface temperature sensor, again you should know the temperature sensor interface. Temperature sensor, it comes into electrical output. So that electrical output we need to convert it to digital. Then only we can see some temperature changes. So that is called like sensors, input sensors. So here you will have input, and in between you can't directly connect it to your microcontroller. We should have conditioning circuit and filtering. Suppose if you see the frequency domain, so we should have like high pass, low pass filter. Unwanted signal, it shouldn't be come to your A to D converter. So like that, you should have one block is input, one block is conditioning circuit. Then after conditioning circuit, to and interface to your microcontroller or microprocessor. That is the level. Suppose if it's a 3.3 volts, and if you are connecting 5 volts input, then your microcontroller might damage. So those compatibility and all we have to carefully look into that. So these are all the like requirement we have to freeze. From requirement we need to develop the hardware, like prototype you can say. So that prototype we need to uh, interface, like you need to communicate, correct? There are so many interfaces, memory chips, and some LCD interface, some sensors interface, some actuators outside interface. All those things needs to be communicated. That is the firmware we'll call. So drivers are firmware. So the firmware software is embedded inside the microcontroller or microprocessor. And then whatever software you embedded, it should be communicated to the external world, like maybe through Ethernet or USB or Wi-Fi interface, Bluetooth. So all these combination is called the embedded systems. So based on application, suppose few like EV application, so they need we have to detect the uh, energy and then convert it to voltage, and then that voltage battery is charged, and then there again BMS will call, like a battery management system. So the battery is charged, correct? So is it overcharged or undercharged, or it is like yet to dry? Those things and all we have to monitor. So all those things needs to be communicated in the system actually. So again, if you see in the embedded system, there are huge domain again, like medical devices, automotive, and like another thing is like aerospace, avionics, IoT, and coming now is AI accelerated things like nowadays. You can see NVIDIA, Jetson Nano is one board is there. So nowadays embedded system, people are telling like it will be not used in the AI. So in AI also embedded system is there, because it's a embedded AI system. So if you see that's now that is the one of the risk nowadays. AI is replacing the jobs and all people are telling. But if you learn embedded systems properly, you can embed your AI algorithms inside the GPU, inside the CPU, and then without internet, it will work. Suppose if your door is open, door or closed, you have to do, and there are multiple doors. So you keep on embedded hardware with GPU, with high speed memory, high speed clock and memory and all. Then you can implement your algorithms inside. And now AI tools, na, everyone is using downloading from cloud, and then and whatever algorithms, CNN, image processing algorithm, whatever algorithms, they are just downloading the library files from there, and then implementing for the applications. So you are not developing any algorithms there. You are not developing any model. So what I'm telling students is, you should develop your own model. You understand the algorithms. Okay, CNN how it works, YOLO algorithm how it works, and those algorithms process you learn first, and then implement in your code. You have to write code from the scratch. Then, and if you develop one model, that's it. So you know how AI algorithm works from the cloud. Same thing you are implemented inside the your board. So what I'm telling is Jetson Nano is the good one, and they have multiple boards in NVIDIA. So you can take those kits and then develop your own algorithms. Okay, and then communicate with different things like home automation. You can develop, and you can do industrial automation. You can do that, and some something tracking, vehicle tracking. So those things you can do. So you keep that module inside that area, and it will communicate. So AI is running there, and you give an interface to your PC or whatever mobile. Then it will be, the algorithm is running inside your thing. So what I'm telling is embedded system is a huge domain, and embedded system with AI also is a big domain. So you, what I'm telling students is, you develop models. Okay, like AI models. You learn the algorithms and then develop on your own, and then those algorithms you can uh, uh, work out. Then you will get good jobs. Like nowadays, the AI companies and all, they need innovative ideas. So those algorithms, if you develop on your own, then you can add some extra features also inside. So that way, my suggestion is you can uh, go for that actually. And coming to the prototype, like PCB design. So I'll just brief on that. So anywhere hardware design is, we need the PCB layout design. So the process is like already Vishnu explained briefly. So I'll go a little bit inside. So first is like the requirements. We have to capture the requirements, and then we have to develop the concept design. So before concept design, and component selection. Once the component selection done, don't go directly to the like prototype PCB layout design. So you develop one breadboard design, and on breadboard you can prove the concept. So maybe you can take the suitable whatever component selected microcontroller, and that boards are available, evaluation boards. Take the evaluation board and prove the concept. So concept, it may not be 100% getting output, but you can prove that. Once it's proven, then after that you can go to the design. Before designing, one simulation also you can do. So for the simulation, we have a lot of tools like LT Spice, P Spice tools are there. So what I told, like in front end and back end VLSI design, there also like Xilinx tools and all available. Same way here also in hardware design, we have the tools, simulation tools. So here you can stimulate the input and then get the output, like timing and rise time, fall time, search. Like if you do the power supply design, you have to see the transit time. All those simulations we can do before designing itself. Then we are very much confident prototype we can go, because in prototype now, if you go directly to the prototype, say like again reiterations. It may not be, unit may not come one time, so it will be one or two iterations. That iteration is again huge money involved, resource efforts involved. So all are like a waste of time actually. So to avoid those things, what I'm suggesting is you can learn simulation tools. So while simulating the circuits, you will be learning the fundamentals of the IC, like components, how transistor works, how diode and how memory interfaces. Like suppose ADC, analog to digital converter, all those things you can, while simulating you will learn actually. So better you try to do some analysis will help. Okay, after analysis, there are few analysis also, like thermal analysis. It's like suppose our unit is having power consumption of something, and it operates in different environment conditions. Like suppose if you see aerospace or defense, it should work minus 40 to 125 degrees centigrade. So your device, you might have selected like industrial component. So that component works at bench in lab level, in our environment condition, it will work. Suppose if you keep same equipment in Himalayas, their temperature is like minus 40 degrees. It will not work. It will fail. So your unit may be catastrophic. Suppose unit is a high risk unit, then we are losing not only our board, we are losing big things. Like suppose if you keep that prototype in that unit in our suppose aircraft. So aircraft, suppose it's a high risk DAL levels is high, then that aircraft is crashed. Then we are losing a lot of things. So those things we can avoid by doing the simulations and all. Okay, and the identifying the components also. Suppose if it is not working, you can go back and look your bill of material, and every stage will have the QC. The quality controller will ensure that you should not avoid the QC also. So that way we can avoid lot of catastrophic issues also. And coming to here, people are thinking like in hardware there is no software. Software is there. That means like firmware, and there are RTOS also. Like OS also used in this hardware design. Like suppose RTOS, we are having lot of threads required, lot of interrupts are there. So to handle multiple tasks, we have to use RTOS. Linux, embedded Linux is a huge domain. So those tools and all we can learn properly, and then you can work with. Embedded Linux is the big domain again. Embedded Linux and the RTOS and VxWorks, QNX. These are the things. And coming to, and you have developed your prototype, everything is ready, and then you have to communicate, correct? So as a hardware engineer, you should know the protocols. Don't take I2C protocol, USB protocol, Ethernet protocol, then you will not learn. So you have to learn the protocols, how I2C interface is worked, and what are the signals, and what is the timing, what is the time or fault time when data is occurred. So if you see there are the standards actually. Everything is defined. Suppose USB 3.0 is defined, the protocol is defined. You just understand the protocol. What I suggest, like algorithms I told, correct, like AI algorithms. Same way, we are having defined protocols: Ethernet, USB, I2C, CAN, PCI Express. PCI Express now high speed actually, like each lane 2.5 gigabits per second. It receives the data and transmit. So those are all defined protocols available, standards are available. Just go through those standards and how it works, and then implement in your design. So that is like firmware again. To come to firmware. So those drivers you can develop, like come in and interface to the external world. Those are the communication protocol. You should learn the communication protocol properly, and then its hardware is very. And then to need all these things, like all these prototype boards, we need power, correct? So again, the power quality is very important. So power quality means like the compatibility, power management we have to do. Power management means what is my load demanded, and we have to calculate from there back to the input. That way, power demand also is very important thing. And power analysis, power quality analysis also very important. And coming to the PCB, once this is defined everything, then we'll go for the PCB layout design. So for the PCB layout design, again we'll be using like EDA tools, like again there Cadence, Arcad, like pads, like the mentor graphics things. Those tools and all we'll be using, and there we have to understand the PCB guidelines properly. We shouldn't directly go, because if it's a high speed PCB, high speed means like my clock speed is like 150 megahertz, and there is a RF front end is available. So here we are having multiple interfaces connected to your microcontroller or microprocessor or CPU or GPU and all. So we have to properly understand the PCB guidelines. Okay, we have to make one checklist properly, and then go further. So we are having the bill of material, correct? So from the bill of material, uh, the footprints, like component footprints, also very important actually. So nowadays models are available, footprint models. If it is not available, we need to create from the data sheet. We have to go through the data sheet properly, and then create the footprint. So to do that thing, like there are two things. One is the schematic design, like circuit design. We'll be using Arcad or something Altium, those tools and all. Or those tools we use for the schematic design. And the schematic design also, we shouldn't complete schematic design and go to the PCB layout directly. There is a netlist. The output is netlist. We have to verify the netlist. Netlist is called like connections. Suppose one PN, one diode is there. That diode anode is connected to something else and cathode is connected to something else. So we have to see the pins, like where it is connected. Those outputs and all, it will be generated. So we have to thoroughly check the netlist. That is pre-netlist we'll call. After schematic, we have to check the netlist. Once netlist is 100% correct as per your schematic design, then that file we will give it to the PCB layout guy. So the PCB layout guy will verify the footprints. All footprints should be exactly matching with your components. If it is not matching, then that component you can't place onto the PCB. Then again we have to go for reiterations. Again there is a cost involved, time, efforts, everything is lost. So that's why, as Vishnu suggested, every stage we need to verify the QA, qualification assurance, quality assurance checks and all we have to do. like netlist also, suppose I am designing, I shouldn't do the netlist checking. I should give it to third person. So that person will find out the errors. Then he will suggest me. Suppose I am designing, I may bypass because it is okay like that. It shouldn't be like that. So what I'm telling is netlist thoroughly verified, and then footprints also properly created, and then we have to see the PCB dimension. Suppose the overall system, what Vishnu shown one system, correct? LRU he has shown. In that there are multiple PCBs are there. So those PCBs properly should be inserted. If I am not able to insert and connect to the motherboard, then that PCB is out. I can't use in the LRU. So we'll have to properly see the system requirements. System, that is called system requirements. In system requirements, again we have the called the dimensions. So my PCB dimension should be this way. This is my PCB dimension. In that, we have to place the components. If I am not able to place the component, we may discuss in the system level, and then maybe another board we have to develop, or that board goes to the system. So all these requirements needs to be freezed before going for the prototype development. So that is PCB dimension we are fixing, and then component placement also very important. So we shouldn't, few critical signals are there. Suppose one clock or LVDS. LVDS like differential signal, or it has pair actually. It's like plus minus, the positive negative. So those are the LVDS signal. Suppose if you see USB having D plus D minus. So those are the very critical signals. You have to place properly. It shouldn't be crisscross. It shouldn't go layer one line, layer 3 and layer 4 another line. It shouldn't be like that. So those are the critical signals. These are all guidelines we have to follow. So we have to make nice guidelines document, and it should be reviewed various knowledgeable person, and that guidelines we have to implement in your PCB. Okay, and then based on current also, like current consumption also, we need to see the track. Track means like if you see the PCB, there are so many lines connected, correct? So microcontroller having 48 pins means 48 connections are there. Those connections we have to see properly, and then the trace width, trace length, all needs to be matched. So if you see like single-ended signal, single-ended means 0 to 5 volts or 0 to 3.3 like that. Those are single-ended signals. So those signals, it should meet the impedance. So if impedance is not matching, there is a propagation delay. Once propagation delay is there, suppose I want 3.3 volts, I may get 2 volts. So as per logic, 2 volts is low. It should be about 2.5. So my required desired output is missing. So that way it will miss actually. So the trace width, trace length, and all those things are very important. Though, so like driver, one like source and receiver, or transmitter receiver, we have to make the impedance matching for the single-ended signal. Suppose if it's a differential ended signal like T plus D minus, it should be 100 ohms impedance should be matched. So based on your design, PCB design, few things we can't avoid. Okay, I'm not getting 50 ohms. I'm getting maybe 40 ohms. So, but my design, there is no alternate option. So to fix the 50 ohms impedance, in PCB also there are like fabrication wise, PCB fabrication will call, correct, the manufacturing. In that area, we can match the impedance. So that is like pre-peg will call. So pre-peg. So pre-peg means the conductor and another conductor, there is a insulator inside. So if you have 4-layer PCB, so first layer is like signal layer, second is ground, third is again power, fourth is again signal. So the signal layer and ground layer should be properly insulated. So based on the material, like FR4 material or epoxy, those materials are there. So those material thickness, by changing or by adding or decreasing thickness of the prepeg, we can match the impedance. Okay, that is again guidelines. They should know, like PCB layout guy, he should know the how to fix the impedance. So how to find out the impedance is coming or not? We have to do the SI analysis, will call signal integrity analysis. So once the layout is finished, everything routing is done, and then the output will be giving it to the SI guy. So the SI person will stimulate the signal. Stimulate the signal means, suppose I am having data, like DDR memory is there. I am having like 4096 locations. We have to fill some data, and that data is properly coming or not, and storing inside or not. So the throughput is coming or not, the bandwidth is okay or not. Those things you will verify. And the power analysis, like power also, is there any surge is there, and is there the impedance matching is done or not. The 50 ohms single-ended signals 50 ohms is coming or not, and differential signal 100 ohms is coming or not. So he will suggest actually, oh, one signal, one pair is not getting 100 ohms. I am getting only 80 ohms. So he will suggest. So and so signal failed, but routing is completed, and there is no alternate option to change the routing. Then the PCB layout person or designer, he should properly guide it to the fabrication guy. So he will add the pre-packed components, the material. Based on that, with that he can match the impedance. Okay, and there are few crosstalk, all those things. So there are a lot of guidelines, PCB guidelines. IPC standard is there, so you have to go through the standard. So in hardware, every sector we are having standards. So you have to properly understand the standards and then implement during your design. So once PCB is fabricated, we will get the components, like a pair PCB will get. There is no component, only placement, like symbols. Suppose one microcontroller is there, it has symbol and it has pins and all, and connections and all, it will be shown. So we are having BOM, correct, bill of material. So take the bill of material components and then assemble. So nowadays, complex boards will be assembled in automation actually, like pick and place machine. There is a huge area. That area also is big in India now. Actually, China is the bigger player. Now India is also improving actually, and there are a lot of pick and place missions, and then here also lot of checks. First is the if you see pick and place that automated assembly area, there are big units like what you call printer. Suppose if you want to solder any item, we have to place some glue, what you call the paste. So that paste you have to keep onto there are pads. So on those pads we have to solder the pin, correct? So first is the PCB you have to pass into the printer. So there the paste is pasted on the wherever the pad is there, the paste is applied on that, and then it will go to the pick and place mission. In pick and place mission, as per BOM, we will be keeping all the parts in the trace. Okay, so the machine we have to program actually properly. So whatever coordinates, some 0, 0 to the distance, whatever the PCB dimension, everything we need to program. So once the components and programming done, automatically it will pick and place the components. Nowadays, 100,000 CPH are there, like 1 lakh components at 1 hour, components per hour. Okay, we have arms. So here also there is a huge robotics and all there involved. So mechatronics, I think one Sabat explained about mechatronics. Mechatronics again involved in this area. Okay, and then components is placed on the PCB. Then it will go to the oven. Oven is like soldering the components and all. Once it's soldered properly, and we'll have the inspection, like AOI inspection, X-ray inspection. Few components like BGA is there. BGA is balls inside the chip that we can't see. Is it properly soldered or not? We don't know. So those and all we can verify in the X-ray machines. And AOI like 2D parts and all we can verify in the AOI machines. And once verified all the things, and then it will go to the testing or QA. Once QA is cleared, the PCB is ready. So that PCB will go into your LRU or your system. So this is the whole process from requirement to the PCB assembly. Once PCB assembly is done, once it goes to LRU, then it will go for the testing. I think those things, everything is covered by Vishnu, I think, LRU and all. Yeah, I think, and coming to domain, I think here also we have a lot of things. And for the C, and one thing I forgot actually, for firmware development, we should have strong knowledge in C language, C++, or and assembly language. These three very, very important to develop your firmware. Firmware is like interface. Okay, physically is it connected or not, or protocol implementation, or memory interface, sensors, actuators, or your communications like Wi-Fi, Bluetooth, Ethernet. All the things. If you want to test with your code, we should have the strong skill, strong knowledge in C, assembly, and C++. Okay, these are the tools, and you have tools like GCC, Keel compiler, IAR, okay, VS Code, and yeah, and few debuggers are there. So nowadays, if you see the debugger, you can see the interface is properly connected or not. The memory, suppose ADG is there, you know the sampling frequency, and then we are reconstructing the frequency. Suppose you got like 20 kilohertz, so 20 kilohertz reconstruction is properly done or not. Those things and all we can verify using the debuggers. So like Keel, suppose you see analog devices, we have Visual Studio. And TI Code Composer and ST Microtrans. Like nowadays, lot of these companies having the own debuggers, typically emulation they'll call. Okay, through JTAG. Again, JTAG standard you should know. So how JTAG works, what are the signals? Okay, using that it will be connected to your PC, and in PC your Keel compiler or TI Code Composer, those tools are there, and then through JTAG your hardware is connected and you can debug. So before going to the LRU interface or system interface, you can properly test board level itself and implement your software and then flash it. So your code is flashed inside the microcontroller or flash memory. Okay, and whenever power goes, also it will be your code is running. Okay, so that way those tools you can use and implement your what you call the firmware and all. Okay, and here in hardware, major thing is you should have again strong digital logic fundamentals, analog signals or analog circuits design, and then PCB fundamentals like PCB guidelines, and then analysis. These are the very, very important to develop the hardware actually or embedded system. Okay, so yeah, and coming to job thing, main thing is like if you involve from the second year. Actually, I am having MOUs with JNTU and a few colleges also. Actually, this is my fourth batch. I am getting every year students from second year itself, and I am involving those guys in my projects, like whatever R&D projects I am doing. So I am giving small module, and then I'm explaining what is the system, and in that one module I am giving to them, and they are developing. So they are learning, like 4 months they come, and after 4 months they got selected big companies and all, and few guys retained in my office itself. So that way, every year I'm giving internships. Okay, and I'm not just calling them and time pass. I'm involving in the design, like whatever design I'm doing, whatever services I'm doing, I'm involving those guys in the design itself, and they learn things like from requirement to evaluation. The whole process they learn, and few guys they initially they told I want to be in software, and after 4 months training, his interest is hardware. I don't want to move software, sir. I want to be in hardware. So that way, most of the students, they doesn't know the hardware thing actually. If you jump inside, it's a very interesting thing, but you should have patience. Without patience, like it's a doctor. Hardware is a like doctor. So if you do mistake, it will be reiterations and a lot of catastrophic issues might come. So hardware, we should have a lot of patience, and then, and it's a continuous. It won't be like software might be job losses might be there, or some recession might happen, they remove, but hardware is always there. Electronics is everywhere. Okay, now, so in AI also there is a hardware. So everywhere hardware is involved. So you choose like which area, like semiconductor side, or embedded systems, or AI. And if you see the domains like consumer electronics, aerospace, automotive, industrial automation. Now industrial automation is huge revolution. Now workforce is very problematic now. Okay, and the latest technology, whatever existing employees, they doesn't know the latest technology thing, because everywhere electronics and lot of IoT and all involved, and like there again automation is a huge domain, like automation, like IoT, Internet of Things. Okay, so everywhere electronics is involved actually. So that is another domain, industrial automation. Okay, and the medical. In medical also, we are doing almost 4 5 products now. So those products, there is a huge thing again, like image processing. Okay, and see a lot of diagnostic equipments, a lot of surgical equipments. If you see surgeon, like robotic surgery, you see there is again electronics involved, and there is the cut cog and things are there. Suppose if you want to remove the skin, doctor use some instrument. There is a cut. It ignites actually. It ignites means it will use some spark ignition. Okay, with that you can cut the skin. Okay, and then once you remove, and then there is a blood vessels, correct? So we need to cut cut once you cut, the blood may flow, so we can stick that. For that again coax, so there is a stick. If you put both nearby, again some spark ignition comes, and then it will, your vessel will be closed, then blood won't flow. So like that, there are a lot of electronics there. So everywhere electronics is, medical is a huge domain again. Okay, and then automotive, EV sector, and solar energy. So everywhere electronics is there. I have to properly choose and then improve your skills. So my suggestion is, from secondary itself you start, and then by fourth year you know whole process, how industry works, how industry takes the employment and all. So normally if you join in any company, it will take a minimum 2 years to jump into work. So but nowadays even students coming from second year, I think internship started. 1 month internship is there in second year itself, and fourth year they are giving 4 months internship. So it's a mandatory, it seems. So my suggestion is, better go to industry and then learn things, and then you choose your career, which side you want. Okay, yeah, that's it. Thank you.
Yes, sir. Thank you so much.